Okay, welcome back everyone. In this video, I want to talk about something that most of us have kind of taken for granted the first semester, or at least the first time we see it. We just kind of, you know, accept it and that's the way things are and don't really think about it too much. And what I'm talking about is the constant little g of 9.8 meters per second squared, with a negative sign if you feel like it, to show that it's down. So this is what we commonly call gravity, but that's really not 100% accurate. Instead of calling this gravity, well, we should first of all be talking about the force of gravity. And remember, for the force of gravity, by this point we know that it's not as simple as just mg, it's actually gmm over r squared. Okay, but don't worry about that right now. The thing is, we are used to talking about this acceleration due to gravity of 9.8, but we don't really talk about where it actually comes from. And it turns out that it does in fact come from the gravitational force. And we know from previously that Fg, gravitational force, is mass times gravity, and so it makes sense that little g, our acceleration due to gravity, is the force of gravity divided by some mass little m. Okay, but that doesn't really mean a whole lot. So let me draw a picture for you. Okay, so here is a chunk of the Earth, and here's a little astronaut dude. Let's say this little astronaut has a mass of little m, and the Earth has a mass of big M. So what we can do is, at any point, we can draw the direction of the force of gravity acting on this little dude. For example, right here, it might look something kind of like this. Alright? And the thing is, we have to be careful about this force of gravity. It's really equal to the gravitational constant times the mass of the Earth times the mass of the guy, all over his distance from the center of the Earth squared. So hopefully you remember that this r is the distance from the center of one object to the other. So when we're talking about the Earth has a radius. The radius of the Earth is like right here. That's RE, radius of the Earth. And if this astronaut dude is at a height of h above the surface, then his true height is the radius of the Earth plus h. And that's what would go in here. Okay, but anyways, the point is, that's the force of gravity acting on him, right? So that should also be equal to his mass times g, little g that is. And as a matter of fact, when we stand on the surface of the Earth, so let's put him down here so that h is 0 at the surface of the Earth. When we put him down there, we can calculate the force of gravity, and that's actually equal to the force of gravity. It's just the same force being written two different ways. So on the left is the so-called universal law of gravity, and on the right is his mass times little g. Okay, so now hopefully you're noticing that I keep writing the same thing over and over, but I'm not doing what should be obvious, and that's crossing out little m, his mass. Okay, now what this leaves us with is little g, which is the gravitational constant, the mass of the Earth, and if you're standing on the Earth, this is the radius of the Earth squared. Okay, so this little bit right here is on the surface of the Earth. And if we do some nifty things here, for example, we know the gravitational constant is 6.67 times 10 to the negative 11th. I'm a nerd because I have that memorized. Okay, the mass of the Earth is about 5.98 times 10 to the 24th kilograms. Yes, I'm a nerd for knowing that one. And the radius of the Earth is about 6.38 times 10 to the 6th meters. Okay. And so when you take all three of these constants and you plop them into this equation, what you get is 9.799 meters per second squared. You can check the units if you don't believe me. And guess what? That is where our beloved 9.8 comes from. This is the acceleration at the surface of the Earth. It's the acceleration due to gravity. Another way to think about this is that acceleration is force over mass, right? F equals ma. So the acceleration caused by gravity is equal to the force of gravity divided by the mass that's doing the accelerating. Okay? Now you could turn this around and you could say, well, Mr. Brow, what about for the Earth? And, well, if you do that, you'll find the acceleration that the Earth takes if you divide by big M, and you're going to find that that's not 9.8. Because if you drop something on the surface of the Earth does not accelerate up with 9.8. And we know that even though the forces are the same, here's the Earth, here's a little dude, even though these forces are the same, well, force is equal to mass times acceleration, and the mass of the Earth is vastly different from the mass of the guy, so they have vastly different accelerations. And we talked about this during Newton's third law. Okay, so in general, if you want to find the acceleration due to gravity, okay, this is g, and this can be done at the surface of any planet. It can be done in orbit, but you take the gravitational constant, you take the mass of the planet, and you divide by the radius of the planet plus the height squared. So if we're talking about something at the surface of a planet, h is equal to 0 at the surface. Okay, now this also leads us into something that we call the gravitational field. And the gravitational field basically is a couple things. One is it's a map of all of the gravitational forces acting on an object. Okay, so up earlier, let me scroll back up, when I drew a picture of the force acting on that little astronaut dude, well, I didn't have to draw him there. I could have drawn him over here, or over here, or over here, or even, in some cases, right here, you know, if we dug a hole or something. And in all of those cases, there would be a corresponding gravitational force. And if you're kind of at the same radius, it'll be approximately the same force. Of course, this one out here is a little bit less. And if you could dig into the Earth, well, it'd be more complicated. It'd probably be slightly larger. And that's because you're closer, but then you also have less mass affecting you. Okay, well anyways, the moral of the story is that this gravitational field, the map of all of the gravitational forces, is defined by little g. Little g is the value of the gravitational field. So it's the force of gravity divided by the mass m. And this m is what we call a test mass. In other words, if you think about the astronaut floating around the Earth, is his mass going to have much an effect on what happens to the Earth? No, not at all. It's 10 to the 20 something times less massive. So when we test or try to figure out the gravitational field of an object, we take a test mass which is very, very small, so it doesn't sort of upset things. Okay? Could I, for example, take the Earth right here and place it, you know, next to the surface of, let's call this the surface of Jupiter? Would that be a good way to test out the Earth's gravitational field? Well, no, because Jupiter's mass is so huge, much, much larger than the Earth, that the Earth would start moving and you wouldn't be able to figure out the Earth's gravitational field. Now, the reason that I introduce this concept now is partly to underline the importance of the gravitational field constant, which we know is 9.8, but also as kind of foreshadowing for when we get to electric charges and electric fields. But more about that next unit.